Welcome. We're now going to have a look at the torque on a coil. So we're going back away from Faraday's law of induction, and we're going back to his motor effect. So this is the torque on a coil. Before we start, let's just revise what is torque. Torque is the turning effect of a force. So it's the turning effect of a force. It's been given that letter tau, and it is equal to the force multiplied by the distance away that the force is from the centre of turn. So if I've got an object here, and I'm going to pin it here, and I place a force here, and it's act at d distance there, then the torque would equal F times d. If you're having a bit of trouble at this stage and say, oh, I don't remember this, could you pause the video and go and have a look at your notes on torque and then return? We're going to now have a look at the torque on a coil due to the motor effect. Okay, so we're going to we're going to have this force here be replaced with the motor effect force. So, just a few notes before we get going. In a magnetic field, any current carrying conductor will experience a force. We know this as the motor effect, and this force is equal to, it's all different order these days, it's B, I, L, and it, if it's not at 90 degrees, then it's a sine theta at the end of that. If the conductor is in the shape of a rectangular coil, then the wires crossing the field will also experience a force, but in opposite directions. So what does that mean? So here we have a north and a south pole, and so this is a bar magnet, a north pole and a south pole, and the lines of the field lines will go from north to south. Now, I drew this, and I didn't make these magnets very big, so just assume the magnet is as large as it needs to be there, please. Okay. Now this, I have a single loop of wire here, and we've got a current going in this direction, so the current is going through and around this direction and down this way. Okay. Looking at this wire here, we'll just go A to B, so wire A to B here. We've got a magnetic field which is going this direction. So we've got B going in that direction. We have a current, the current I'll put as brown. We have a current going that way, and using our FBI, our right-hand push rule, we can indicate that this is going to be into the page. The force is going to be into the page on that one. The current continues around from there to here. Now on this one here, the current is running parallel to the field. So the current is parallel to the field, and as a result there is no motor effect, there is no force on this wire. Okay, so this wire, even though it's drawn as if it's out of the field, but as I said before, just assume that these are quite large, these magnets, there is no field, so no force on this wire here. But when it gets around to here, the current is running in this direction here. So going through our forces again, we've got B in this direction, we have the current in this direction. Using our right-hand push rule, our FBI rule, and that would be the current going down, we get force out of the page. Now, the current that is running in this direction here and this direction here, as it first comes in and is on the way out, once again, the current in this wire here, that one there, is running parallel to the field, and therefore, once again, no force. So we have two forces only. We have a force on this wire, the AB wire, and I didn't write CD, but there's that wire there. And notice that this one is into the page and the other one is out of the page. Here is our axis of turn. So here's our axis of turn there. If we were to grab this force over this wire over here and this one here, and I was to pull this one out and this one in, we would twist this coil. We would twist it so that this one would come out and that would come in, and we would get a turning effect. And this would be torque. So we'd get a push in and a pull out. On that way, would give you a torque. Looking on side on, so we can actually have a look in 3D here. It's the same situation as before. We have, do I have them going in the right direction? Out of the page, so the page would have been down here. So that's the out of page and that's the into the page. And we'll get a twisting in this direction. A torque, a turning of that one there. Right, so together we get two torques on either side of this coil causing a effect. Okay. Now the actual torque on this coil is given as NBIA sine theta. And I'm going to explain all of those once I derive how this formula comes about. So firstly, let's get rid of this sine theta problem. Because that, as you know, will be to do with the angle that this coil would make. It's always been our problem with the sines and the causes. So how do these things work? Okay, how do I get this formula out of this diagram here? Now, the first thing we need to remember is it is all about F equaling BIL and sine theta. But once again, let's forget about the sine theta problem. We'll get all to do with the angle later on. So what is B in both cases? B is the strength of the magnetic field coming out of here. I would be the current going in and out. Let's make the current go the right way for these things. And A, I'm about to show you what A is. A is actually the area of this coil. Over here, L is the length of the wire, so that is L there, and this here is D. Okay, so sorry, I've got to find a little space. I'll just rub this out so I can have some room to work with. Okay, so looking at the coil on top, this here is D, so this length here is 2D, okay? And this is L. So the area of this coil is 2DL, okay? So let's have a look at what is the torque on this coil. So when we come back, we'll know that 2DL is another way of saying the area of the coil. So we have the torque, and the torque is equal to F times D. Now there are two torques here, so it will be 2FD, because there are two torques, one up there and one down here. So that's the total torque. That's the torque formula, and this is the torque on the coil. So it's 2 times F. F is BIL, sine theta, so come on, BIL, and then times D. And if we bring the two together, we get 2LD BI. We noticed a few moments ago that 2LD is the area, so this becomes ABI. So the torque on this coil is equal to BIA. I'm going to put it in that order because it reflects the actual formula that we're going to be using in a few more moments. And this is for a single loop. If there were two wires here, this would be double that torque. So the torque would be NBIA. Okay. Right, so the formula that we're about to use for the torque on the coil is going to be torque equals NBIA, and you're just going to trust me for the few moments, it is sine theta. And what is that theta? In a few more moments, we'll talk about which angle is what. As we always know, sometimes these angles are not nice to work with, especially with induction, and in this case, it's not also not nice to work with. So let's just have a look at what happens to the force and the torque as this coil does rotate. So as we just said before, this is forced up and this is forced down. This coil is going to rotate in that direction. Because the motor effect is F equals BIL, I'll just say sine theta. The force here is on the wire that is running backward. Okay, so this is the wire running back. This is the front of the coil. This is the two little places that it's coming in. So just make sure we can see. We are seeing this wire here side on. Okay, and the two little dots you're seeing here are those dots going in where the current is coming out and going in. So going back, those there are where the coil, that's the coil side on. Those are where the current is going in and out. And this is the coil flat, and we're seeing the edge of the wire here and the edge of the wire there. So that wire runs into the page here. Now, as a result, it is at right angles to the field. It is also at right angles to the field here. See, the force is at right angles and right angles and right angles. So it's always going to be sine of 90, which is 1. So the force here is always BIL. The magnetic field strength is the same, the current is going to be the same, and the length of wire is the same. So it doesn't matter, as this coil turns in its anti-clockwise motion, this force, the motor effect, is going to actually be the same. What is going to change, however, is the angle that is being made with the coil and the magnetic field. Here, the coil, now we'll just do with the plane of the coil at the time being. The plane of the coil here is that one. We'll say orange, and I'll do with this one here, it is that purple. Okay? So as it turns, the angle is going to change. Here we are really getting a nice 90 degrees between here and here. And as a result, torque, as we know, is FD sine theta. And if it's 90 degrees, it's going to be maximum. Okay? So there's maximum torque on the orange coil here. As it turns, the angle is going to become more and more towards 180 degrees. And as a result, the torque is FD sine 180 with this one here, then the torque on this is 0. So torque, just move that up slightly. The torque is maximum when the coil, the plane of the coil, is running with the field. And the torque reduces to 0 when the coil becomes vertical within the field. The torque is max in the horizontal position. So going back here, there we saw the torque is maximum because the angle between the force and the field and the actual displacement from the center of the turn outward, that is at 90 degrees, and it becomes 180 at the top. So torque is equal to NBIA sine theta. Okay, and we want the torque to be 0 at theta equaling 180 degrees. So the angle that we're going to be talking about is the angle between the plane of the coil and the direction of the force. Okay? So how are we going to measure that? So it's going to be the direction of the force that we have to constantly do. So as a result, we need to come up with a way of working out what this theta is going to measure and how is it going to measure it easily. So when it is vertical, let's just recap, when it is vertical, the coil is vertical, we want to talk of 0, and when it is at right angles to the field, like that, in the horizontal to the field, we want a maximum value. So let's go through and see what we can do here to try and get this formula to work, or get a formula that works. So here we have, once again, we've got this coil down here, a north and a south, exactly the same as we've just been having here. It's the same as the last setting up, so I haven't changed anything. What we need to come up with is a way of measuring torque equaling NBIA sine theta. What is this theta? Because we've defined everything else. N is the number of loops, B is the magnetic field strength, I is the current going through, A is the area. What we're going to measure here. Okay. So what we are going to do is we are going to look at a tilt. So let's make this tilt a tilt of alpha to the field. So here's the field going across there. Okay. So that angle there is going to be alpha. And that means the angle between the plane of the coil is alpha. But we want, going across here, alpha in this case here would be 90 degrees. And alpha, in this case over here, would be 0. Okay? So, we've seen this before. We want it to be the opposite of what we've got. So we want to use the cosine function, but in fact we're locked with the sine function. So what we want to do is we're going to find that theta is going to be formed as the angle between the normal and the normal to the plane and the field. So there's theta there. Okay. So theta would equal 90 minus alpha. So theta is the angle between the normal and the field, and alpha is the angle between the plane of the coil and the field. So let's just find that. Alpha is the angle between the plane of the field, the plane of the coil and field, and theta is equal to the angle between the normal to the coil so the normal to the plane and the field. Technically, theta is actually the angle of the area vector, but we won't go into that too much. It's just that's a technical term with this. So there are two ways that you're going to be asked questions. You're going to be asked questions about that the coil is horizontal with the field, and then you'll say, okay, alpha in this case would be 0, and therefore it's going to be 90 minus that 0, and so on. But we'll deal with that as we come. Okay. So theta here, notice it is theta, and theta is the angle between the normal and the plane to the field. Sorry, the plane and the field. Okay. Right. So, sorry, I don't need that one anymore. Okay, so let's just try a question by ourselves firstly. A coil which is 5 times 4 with 15 windings is placed horizontally in a magnetic field of strength 12 Tesla. What's the torque on the coil? So let's just do a sideways from the top. So there's a north and a south. Okay, the coil is 5 times 4. There's both centimetres. I haven't given you a current. I have to give you a current. So let's just say I equaling 2 amps. Okay, sorry, that was my fault. And the field strength is in this case, is 12 Tesla. So T equals NBIA, and it's sine theta. And we'll come to theta in a few seconds. So let's work out all the values so far. N is the number of windings, so it's 15 windings. B is 12 Tesla. I've just told you, is 2. A, remember A has to be in meters, so it's 0.05 times 0.04, and that will give us, just making sure I get the right number of zeros, 0.5 times 0.04, and that gives us 2 by 10 to the minus 3, that's 0.002 meters squared. Okay, right, now horizontal. So looking side on, here is the north, here is the south. If it's horizontal, my alpha is equal to 0. Okay, remember alpha is the plane of the coil, the sideways looking of the coil, and the field. So the field is going north to south, so there's the field. And the angle between my blue line, which is the coil, and the field is 0. So theta is equal to 90 minus 0, which is 90 degrees. Now remember, we want torque to be maximum, and maximum torque happens in the horizontal position between. And remember, sine of 90 degrees is equal to 1, which is the maximum value. Okay? Putting in those values, we get torque equaling 15 times 12 times 2 times 0.002 times sine of 90, which is 1. That's good because we know it's in the maximum position. And popping those values in, 15 times 12 times 2 times 0.002, we get 0.72. Now, don't forget what are the units of torque. It's the Newton meter. Okay. So don't forget to put, it's quite important to put your units on everything here. Let's try another one. I'm just going to change this one here. I've just thought I'm just going to change this one here to not be 45, but I'm going to make that 30 degrees because 45, alpha minus 45 is going to be 45. Okay, so here we are, a coil with an area of 30 centimeters squared, placed at an angle. Have I given you the current again? No, I haven't got the current, so I'm going to give you a current. Let's make I equals 5 amps this time. Okay, so it's area 30 centimeters squared, placed in at an angle to the magnetic field. So this is the angle between the plane of the coil and the field. And the torque on the coil in this position is 0.8 Newton meters. What is the strength of the field? So once again, drawing a little diagram, north and south. Our coil is tilted, and this time the tilt angle is 30 degrees. Okay, so that's the tilt angle. So alpha equals 30 degrees. Okay. The current equals 5, and the only hard part is the area equals 30 centimeters squared. So we have to convert this to meters squared. So let's just do that. A quick way of doing 30 centimeters squared would be 30 centimeters squared would be 30 centimeters by 1 centimeter. This would be 0.3 meters by 0.01. And that is 0.3 times 0.01, and you get 0.003 meters squared. Okay, we know what the torque is. We're going to be working our way back this time. So the torque is 0.8 Newton meters, and we're asked to find B this time. So, going through, always write down your formula, NBIA sine theta. The torque is 0.8. The number of windings in this coil is not given, so we have to assume 1. Times B, which is what we're trying to find. Current is given as 5 amps, and the area is 0.003 times now theta. We know that alpha is 30, and remembering that theta is equal to 90 minus alpha, so it is sine 60. Rearranging, we get B equaling 0.8 over 5 times 0.003 times sine 60. And putting that into our calculator, that's 0.8 over 5 times 0.003 times sine of 60. It's 61.6 Tesla. Okay. There is now a worksheet that I will help you through, so have a go, and the link for that worksheet is in the description on Compass. Thank you.